Techniques for finding limits. We're going to demonstrate many examples, starting with the limit of 2x plus 3 squared as x approaches 1. The first technique that should always be tried for finding a limit is simply substitution. Since x is approaching 1, simply replace x with 1. Two times 1 plus 3 is 5, and 5 squared is 25, and that's the answer. The next example is find the limit of x squared minus 4 over x minus 2 as x approaches 2. In this case, when we replace x with 2, the numerator will be 0 and the denominator will also be 0. When this happens, we call this an indeterminate form. Indeterminate form. And we will find the limit by first simplifying x squared minus 4 over x minus 2. We'll say this is equal to the limit of x plus 2 times x minus 2 over x minus 2 as x approaches 2. And this becomes the limit of x plus 2 as x approaches 2. That's because x minus 2 divided by x minus 2 is 1. And then the limit of x plus 2 as x approaches 2 is found by substitution. That means replace x with 2. So the limit of x squared minus 4 over x minus 2 as x approaches 2 is 4. So factoring is another technique. Then the next example is find the limit of x minus 9 over the square root of x minus 3 as x approaches 9. And like the last example, if x is replaced with 9, the numerator and denominator will both be 0. That's called the indeterminate. The technique for this is called rationalize the denominator. So I'm copying the symbolism. The limit as x approaches 9. X minus 9 over radical x minus 3. We're going to multiply this denominator by its conjugate, radical x plus 3. If we do this, we must multiply the numerator by the same thing, radical x plus 3. We're multiplying the numerator and denominator by the conjugate of the denominator. So we now have the limit as x approaches 9. This denominator, when we multiply radical x minus 3 by its conjugate, we get x minus 9. And the numerator, I'll just copy that, x minus 9 times radical x plus 3. This is now equal to the limit as x approaches 9 of radical x plus 3. Because x minus 9 divided by x minus 9 is 1. And now we can evaluate this limit by substitution. What I mean is replace x with 9. So we get 6 is the answer. 6 is the limit of x minus 9 divided by radical x minus 3 as x approaches 9. Next example, the limit of 1 over x plus 3 minus 1 over 3, all this over x, and x is approaching 0. If we replace x with 0, the numerator will be 1/3 minus 1/3. And if we replace x with 0, this denominator will be 0. The technique for evaluating this limit is to simplify this complex fraction. Copy the limit as x approaches 0. We're going to multiply the numerator, that means above this purple line, by x plus 3 times 3. And because we are doing that, we have to multiply the denominator that's below the purple line by the same thing, x plus 3 times 3. So similar to the last example, we're multiplying the numerator and denominator by the same thing. That's what we did here. We multiplied the numerator and denominator by this red. Here we're multiplying the numerator and denominator by this red. The limit as x approaches 0. When we multiply this red times 1 over x plus 3, we end up with just 3 times 1. And then there's this minus sign. When we multiply this red by 1 over 3, we get the 1 times the quantity x plus 3. In this denominator, I'm just going to copy that 3x plus 3 times x. We will now distribute this negative 1. Limit as x approaches 0. 3 minus 1x minus 3 all over 3 times x plus 3 times x. So we just distributed to get this. Then we see 3 minus 3, which is 0. We now have the limit as x approaches 0 of negative x over 3 times x plus 3 times x. The x up here and the x down here cancel. That leaves negative 1 in the numerator and 3 times x plus 3 in the denominator. Now we can replace x with 0, since this is the limit as x approaches 0. And when we replace x with 0, we get negative 1 over 9. That's it. Okay, next example is the limit of sine x over x as x approaches 0. This is another 0 over 0 form. The sine of 0 is 0, and when x is 0, the denominator is 0. The technique for evaluating this limit is to look at the graph of y equals the sine of x divided by x. You can graph this with a graphing calculator, and it looks like this. And you can see that if x is very, very, very close to 0, like right here, the value of the function is right here, practically 1. That's if x is close to 0 on either side of 0. So here's another x value that's really close to 0. the value of the function is here. And I might have said the value was 0. I misspoke. The value of the function here, that means the y value, is practically 1. The y coordinate of this red dot is very close to 1. Same with that one right there. So we say limit of sine x divided by x as x approaches 0 is 1. And sometimes we have to find the limit of a piecewise function. For example, find the limit of f of x as x approaches 1 if f of x equals 4 minus x squared when x is less than or equal to 1. F of x equals 3x when x is greater than 1. We evaluate this limit by evaluating the one-sided limits. That means we find the limit of f of x as x approaches 1 from the left, and we find the limit of f of x as x approaches 1 from the right. If we get different results, then we're going to say this limit up here does not exist if these come out different. But if x is close to 1 on the left, then f of x is 4 minus x squared. And we find the limit of 4 minus x squared as x approaches 1 by replacing x with 1. 4 minus 1 squared is 3. And we find the limit of f of x as x approaches 1 from the right when x is on the right side of 1. F of x is this, 3x. And we find the limit of 3x as x approaches 1 by replacing x with 1. 3 times 1 is 3. Because these are the same value, the limit of the piecewise function as x approaches 1 is 3. If we did not get the same values here, we would have said the limit of f of x as x approaches 1 does not exist. But in this case, the limit does exist. It's equal to 3. All right, one more thing for this video is called the sandwich theorem. Sometimes it's referred to as the squeeze theorem, and it says this: if f of x is less than or equal to g of x, which is less than or equal to h of x, for all x not equal to c, in some interval about c, and if the limit of f of x as x approaches c equals the limit of h of x as x approaches c, these both equal something called L, then the limit of g of x, this function that's sandwiched between those two, as x approaches c, will also be equal to L. Pause the video so that you can write this entire theorem down. Example, we're going to use the sandwich theorem to prove that the limit of x cubed times the sine of 1 over x cubed as x approaches 0 is equal to 0. So the proof goes like this. We start by saying the sine of anything is between -1 and 1. It doesn't matter what I have written here. I'll write theta temporarily. I'm going to erase it though. The sine of any angle is between -1 and 1. So this is true no matter what's in that spot where theta is. So in that spot, I'm going to put 1 over x cubed. And now I'm going to multiply through by x cubed. So multiplying each part of this inequality by x cubed turns into -x cubed is less than or equal to x cubed times the sine of 1 over x cubed, less than or equal to x cubed. And now we're going to take the limit of each of these pieces as x approaches 0. The limit of this piece, -x cubed, as x approaches 0. Copy the less than or equal to. The limit of this middle piece, x cubed times the sine of 1 over x cubed, as x approaches 0, less than or equal to the limit of this third part as x approaches 0. So I just rewrote the line above it and put limit x approaches 0 in front of each. And this limit is found by substitution. Just replace x with 0. Copy all this. Copy this less than or equal to symbol. And this limit is found by substitution. The limit of x cubed as x approaches 0 is 0 cubed. So this limit that's sandwiched in between these two, green and blue, must equal 0. Since the limit in the green is 0 and the limit in the blue is 0, the limit of x cubed times the sine of 1 over x cubed as x approaches 0 must equal 0.